Hello and welcome to my presentation of our DCASE 2021 contribution, Self-Trained Audio Tagging and Sound Event Detection in Domestic Environments. This is a joint work of Reinhold Haeb-Umbach and myself, Janek Ebbers. Let me start by giving an overview of our paper. We present our system for this year's DCASE Challenge Task 4, which is called Sound Event Detection and Separation in Domestic Environments. Our focus here lies on the weakly labeled and semi-supervised sound event detection part. We present an advancement of our last year's system, which consists of a forward-backward convolutional recurrent neural network for audio tagging and for strong pseudo-labeling of the weakly and unlabeled data, followed by tag-conditioned sound event detection models. We present several novelties here. We introduce a strong label loss in the FB-CRNN training to better exploit the strong labels of the synthetic data. Further, we perform multiple iterations of self-training, which has shown to improve performance significantly. We explore different architectures for the tag-conditioned SED models, including convolutional, recurrent, and transformer architectures. Finally, we propose a nonlinear score transformation to obtain a smooth PSD walk. In the challenge, our system scored the 4th rank in terms of PSD scores, and it achieved the best performance in terms of color-based F1 score. I will now give some more details about the models used in our system. The forward-backward CRNN consists of a shared CRNN front end, followed by two separate recurrent classifiers, where one classifier is processing the input audio in forward direction, shown here in blue, and another backward classifier is processing the input signal in backwards direction, shown in orange. Let me explain the idea of the forward-backward CRNN with an example. Assume we have an input audio given with an event activity as shown by the green plot. The idea is that the forward and backward classifiers classify active events as positive as soon as they see event activity in the input signal. For the forward classifier, this means as soon as it passes the first onset of event activity, it is supposed to output a positive prediction, which is shown in the blue plot. Similarly, the backwards classifier is supposed to output a positive classification as soon as it passes the last offset of the event activity, as shown by the orange plot. Note that the desired blue and orange signals can only be defined if we have strong labels given. If we only have weak labels given, however, we compute a joint loss for the forward and backward classifiers based on a multiple instance learning criterion, where at each point in time, either the forward or the backward classifier has to classify an active event as positive. If we do have strong labels given, however, we now compute separate losses for the forward and backward classifiers by comparing their outputs with the desired signals shown here. The proposed training scheme encourages the forward and backward classifiers to output positive classifications before they have processed the whole input audio signal. Therefore, at test time, the model can be applied to audio signals which are much shorter than those seen in training. By applying the FB-CRNN to small windows around each frame, we can therefore achieve a sound event detection, as illustrated here in this figure. Hence, the forward-backward CRNN can be used for audio tagging as well as for sound event detection, where the latter is here only used to perform strong pseudo-labeling of the weakly and unlabeled data. With the tags and the strong pseudo-labels provided by the FB-CRNN, we train tag-conditioned SED models in a strongly supervised manner. The tag-conditioned SED model architectures that are investigated in this work are illustrated in this figure. They consist of a convolutional front end, followed by an optional bidirectional RNN or transformer module, and a fully connected classification network, where each of the blocks receives the tags that are provided by the FB-CRNN as an additional input. We observed that our models tend to either output very high scores or very low scores. To still obtain smooth PSD walks and to not underestimate the true PSD scores, we propose to use a nonlinear score transformation to better distribute our output scores over the whole range between 0 and 1. The problem that PSD walks may be underestimated arises from the fact that for computational reasons, PSD walks are approximated using only 50 decision thresholds linearly spaced in the range between 0 and 1. In the figures, we show the approximated PSD walks for one of our models in red, without and with the proposed nonlinear score transformation. The recently published SED scores eval package allows to efficiently compute the true PSD walk, which is shown in blue here. It can be seen that without the proposed nonlinear score transformation, the PSD walk is significantly underestimated when being approximated with only 50 decision thresholds. I now want to conclude this overview presentation by presenting the insights we gained from our ablation studies and the challenge results. In our ablation studies, we found that the proposed strong label loss in the forward-backward CRNN training improves the temporal localization of the sound events. Also, the forward-backward CRNN self-training significantly improves the performance. Further, the recurrent and transformer layers in the tech-conditioned sound event detection models improves performance compared to purely convolutional neural networks. Finally, we found that there is no significant improvement due to even more self-training of the tech-conditioned SED models. In the challenge, we submitted an ensemble consisting of 8 forward-backward CRNNs for audio tagging and 2 for each of the tech-conditioned convolutional, recurrent, and transformer architectures for sound event detection. In the bottom table, we present performances in terms of PSD scores for the 2 considered scenarios and color-based F1 score. We present the results for both the public evaluation set and the non-public official evaluation set of this year's challenge. It can be seen that our submitted ensemble significantly outperforms the baseline with respect to all metrics. However, it is outperformed by the winner system with respect to the PSD scores, but it achieves the best performance with respect to color-based F1 score. Okay, that's it for now. For further details and discussions, we would be happy to see you at the poster.